Okay, so on number 9, we have to determine if these are functions. So we know when we're looking at a set of ordered pairs, well, first of all, with functions, we know that each input should have exactly one output. So when you're looking at ordered pairs, x can't repeat. So notice 5, -1, 5, 3, we have the same x value and two different y values, so 5 corresponds to -1 and 5 corresponds to 3, so 5 doesn't have exactly one output, it has two. Again, if x repeats, we know it's not going to be a function, so the answer here is no. Now if you look at number 10, each of my inputs, that's these guys, does go to exactly one output. 1 corresponds to 0, -1 corresponds to 4, 3 corresponds to 4, and 5 corresponds to 6. It's okay for an x value to correspond to the same value as some other x value, but notice each x value has only one output. So this is a function. On number 11, if you look at all of those points, none of the x's repeat, and so that's definitely a function. Number 12 has lots of issues. It does not pass the vertical line test, so this is not a function. All right, let's move on. So in the number 13 here, we have to find f of 11. So we're going to plug 11 into the f function. So I like to make a little shell or a skeleton. So it's the f function, and wherever you see an x up above, now I have parentheses. And so when I find f of 11, I just replace my x's with 11. And so f of 11 is 11 minus 3, which is 8. G of 11, now we're using the g function. Be careful to always use the correct function. So here we're going to take the square root of our input plus 5. So we're just replacing x with 11 here again. And so this will be the square root of 16, which is 4. Now f plus g of 11, we learn means f of 11 plus g of 11. And in fact, in general, we know f of x plus g of x, f plus g of x is equal to f of x plus g of x. In other words, f plus g of x is a new function that you get by adding these two functions together. But in this problem, it's f plus g of 11, so it's equal to f of 11 plus g of 11. And we already found those. That's 8 plus 4. And so we get 12 here. F divide g of 4 means f of 4 divide g of 4. Again, if there was an x in there, it would have been f of x divide g of x. So f of 4, we can figure out what that is. We plug 4 into the f function. 4 minus 3, we get 1. So f of 4 is 1. To find g of 4, we use the g function and plug in 4. We're going to get square root of 4 plus 5. And that's square root of 9, which is 3. So we're going to get 1/3 here, and so that's my answer on that one. On number 17, we're going to plug in x squared plus 1 as an input into the g function. So let's make a shell for the g function. So again, notice that I've rewritten the g function, but wherever there was an x, now there's parentheses. So if I'm plugging in x squared plus 1 as an input, that's where I'm going to put my input, well, I'm going to put that in the parentheses in both spots here. And so you can see that we don't really need the parentheses there, because 1 times x squared, because that's understood to be a 1 out in front, even though there's no number written there. And 1 times anything is itself. So we can drop the parentheses, and then the 1 and 5 give us 6. All right, let's move on to number 18. So now we're doing the composition of functions. We did a couple of these earlier. Let's see, g of f of 2 That's how we say that. Actually, let me write the functions at the top here first. Those are our two functions that we're working with. So g of f of 2 means g of f of 2. So again, if you can say the left part, hopefully you can remember it and rewrite it as I did on the right side. We say them the same way. Now we're working inside. We know how to find f of 2. We're going to plug 2 into the f function. That's 2 minus 3, which is negative 1. So f of 2 is just negative 1. So g of f of 2 is g of negative 1. We're just replacing f of 2 with what it's equal to. So now we have to find g of negative 1. So we'll use the g function and plug in negative 1. Square root of negative 1 plus 5 is the square root of 4, which is 2. All right, so the next one's f of g of negative 4. So we're going to find g of negative 4. That's negative 4 plus 5. We're going to get 1, which square root of 1 equals 1. So this becomes f of 1. And so now we'll plug 1 into the f function. We'll do 1 minus 3, which is negative 2. G of 20. Now that's interesting. So first of all, this means g of 20. So let's find g of 20. That's the square root of 20 plus 5, which is the square root of 25, which is 5. So g of 20 is 5. We can replace the g of 20 with 5. So now we're plugging 5 into the g function. So it'll be the square root of 5 plus 5, which is the square root of 10. And that's a radical that can't be simplified any further. Remember our perfect squares, 4, 9, 16, and so on. None of those divide into 10, and certainly 10 is not a perfect square, so we're done there. All right, on number 21, this is that situation where we have to put two functions together to form another. In this case, we need to find an h and a k so that h of k of x equals g of x. So this is a little bit different than what we did before as far as the letters that are being used. But what I want you to see here is that k of x is your inner function. So you want to call k of x the inner function. And if you look at g of x here, look at the x minus 5. That's inside. I forgot to put that there. Let's see. So that's inside the radical. That's going to be my inner function. So that's my k of x. Now, if you kind of just cover that all out or x that out, basically you can see what you need to make the other function. It's the square root of x plus 1. So notice when I go to replace x, when I plug k of x into the h function, I'm going to replace that x with x minus 5, and we'll be back to the original function, the square root of x minus 5 plus 1. Actually, let me go back and clean this up just a little bit so we can see it a little bit better. All right, so I do want to mention there's another way you could have done this. You could have chosen your inner function to actually be, whoops, I already did that. Let's see. Oh, I'm sorry, we want to check our answer. If you check your answers, then you'll know that you did it right if it works out. If not, you can try to fix it. So we said h of k of x is equal to h of k of x. And k of x we said is x minus 5. And so we're going to plug x minus 5 into our h function, which is the square root of our input plus 1. And so when we plug in x minus 5, we do get g of x, which was the square root of x minus 5 plus 1. So that works. There is another option that works. You could call k of x the square root of x minus 5. and then h of x would actually be x plus 1. So that's another option that does work. All right, let's move on to 22. It says find the domain in the range. Well, the domain, when you're given points, is pretty easy. That's just all my x values, and we write it in braces. And for the range, we write all the y values. We don't put any repeats, and we normally put the numbers in order. So it would look like that. And of course, on number 23, this is your domain, this is your range. So the domain is just all the numbers in the first set there on the left, -1, 1, 3, and 5. And your domain on the set to the right is 0, 4, and 6. On number 24, certainly we know all the linear equations that are functions have a domain of all real numbers. You can see that if you actually graph this. We know that it's a horizontal line that goes through 2. So certainly the domain is all real numbers. Now the range is a little bit interesting. Aren't all the y values y? I'm sorry, aren't all the y values 2 on this graph? Because every point is up 2. And so this is just going to be the set with 2 in it. There's only one number in our range. All right, let's move on to 25. So in this problem here, if you just had to find the domain, you could set x plus 2 to be greater or equal to 0, because we need to take the square root of something so that we get a real number. If we take the square root of a negative number, we'd be imaginary. So we want our radicand, or whatever's inside, to be greater or equal to 0. But since we also need to find the range, it's easiest to graph this. So if you graph the square root function, we know that's the ET function, looks like that. And we would shift it. Notice the plus 2, we would go left 2. And because of the minus 3, we would go down 3. So I'm going to shift this graph left 2 and down 3. So basically my point at 0, 0 would go left 2, down 3, and it's going to have the same shape. So our domain, notice our leftmost point has an x value of -2, and then it goes forever right, so that would be infinity. And again, we're looking at that lower graph there. The lowest point is going to does have a y value of -3. And it does go up forever, even though it goes up really slowly. So -3 to infinity is your range. On number 26, we actually know the domain of any quadratic function is all real numbers. Oh, I'm sorry, I've got to go. So like I was saying earlier, you could set x plus 2 greater or equal to 0, which tells you that x is greater or equal to -2, which is what we said our domain is. So you can find the domain either way, but if you're having to find the range in a case like this, you're going to want to graph it. So on 26, we said the domain is all real numbers because it's a quadratic equation. If we graph it, it's a parabola. It's U-shaped. But again, if I'm finding the range, I want to graph this. So it would be a parabola that's been moved up 4 because of that plus 4. And so our range would be 4 to infinity. So just remember, when you have an equation, you have to find the domain in range, the range especially, then you're going to want to do like we did here with the graphs. Now on 27, they're only asking for the domain. That's because we haven't graphed one like this yet. We will do that in the future. So in a fraction, and in fact, we talked about how the domain of the functions we've worked with so far are mostly all real numbers, with the two exceptions being a problem like number 25 where we have a radical. We got to make sure we don't take the square root of a negative number. And then on 27, when we have a fraction, we got to make sure our denominator is never 0. So in this problem, x could never equal 5. I'm sorry, -5. Because -5 plus 5 is 0, and we'd be undefined. And so the domain is actually everything else. By the way, you could just set x plus 5 equal to 0 and you get the same thing, but most people just do a problem like this in their head. So our domain is everything except -5, and that's how we would write it. If you were to actually graph it, it would look like that. It would just have one point where it's not shaded. All right, I'm going to go ahead and stop this video here.